Hello, everyone. I am Alban. I will be doing this in English. I'm very, very sorry, but I cannot do this in Korean. um, so, um, I was tasked to talk a little bit about PyTorch and our roadmap and different topics like that. Uh, so, given the other speakers, I'm going to go very quickly on roadmap and high-level ideas we have for PyTorch. And then I will talk quite a bit about backends. And what I mean about backends is hardware, different integrations, and things like that. And I'll finish with select reminders. I couldn't find a good name for this one. It's more general resources or interesting new blog posts that you might be interested in. So the PyTorch roadmap, I am not going to present it because it's hundreds of people working on PyTorch and there is no single unified roadmap. Um, so one thing, a lot of my slides have links in the bottom. You can go there and find information about all of these. But uh, I wanted to basically start this roadmap discussion about the design principles we've had for PyTorch from the very beginning, because I think they are very important and the basis for a lot of the decisions we still make today. And there are only three of them, which are usability over performance, meaning we will always favor the user experience and making sure that everything we do is easy to use, even if you lose a little bit of performance. Uh, there is no point in getting a last few % of performance if no one can use your software. And being able to be flexible, being good, making big changes is more important than the last small bit of performance. The second one is simple over easy, which is an interesting one if you've done software. The idea is we do not need everything to be keys in hand or trivial to use. Everything doesn't have to be a one-liner for the end user. We need something simple that the user can understand how it works and at a glance be, oh, I have a good mental model of what is happening under the hood and I will be able to use this effectively. And finally, Python first. This one is not as relevant today because everything is on Python. But when we started this journey 7, 8 years ago, a lot of the deep learning frameworks were in C++, purely C++, in Lua, in a bunch of other weird languages, and so Python was a big thing. Now I'm going to switch gear a little bit. So I have two hats here today. I am both a core maintainer for PyTorch, and I'm also an employee of Meta. So I also work with Meta. And Meta sponsors a lot of engineers working on PyTorch. So if you're interested to know what the people at Meta contribute and are planning on contributing to PyTorch, there is this post on the Dev Discuss forum that we have that contains the detailed roadmaps for everything that we are planning on contributing to the PyTorch codebase, from core components like compiler and different pieces like that, all the way to more high-level system like documentations, because we now have a documentation team for Edge, for people that want to run on mobile and things like that, or for higher-level applications like TorchTune or Torch Codec. So if you are interested, do go there, take a look. If you have any questions or if you want to give any feedback, you can also answer to post there. And finally, what is my top of mind when I think about all of these different questions and all the different things all these different teams do, I try to give 4 things. But I think the first thing at the top is always stability. PyTorch core is moving a lot. There's a lot of asks from the very different people to do a lot of different things. So stability and making sure that our package remain usable by everyone is the top priority. The next 2 are enable growth, both for backend below and for other libraries above. So we have kind of this interesting thing where PyTorch is in the middle. And so there are things above, things below we need to enable. all of these people. And finally, long-term sustainability. PyTorch is already a very, very big code base. I think we have several millions lines of code. Our testing infrastructure is 3,000 machines, I think, at this point. So there's a lot of things happening. A lot of people want to contribute a lot of things, but we need to maintain them. We need to keep them going for a long time. So this is also top of mind on how do we build a sustainable ecosystem around PyTorch. And so one example of that is a lot of the work we've been doing on backends and how do we extend below PyTorch. So when you write your model, or hopefully most of you are familiar with the idea of like you write your Python script, you write your model, and then when you execute it, it has to run somewhere on something. And so that is what we consider a backend. In particular, it's anything that can be leveraged to run your PyTorch code or model. And that can be very flexible. In particular, it can be a specific hardware, but it can also be different ways to look at CPU, different kinds of CPU, different kinds of accelerator. It can also be sometimes some remote machine, so anything that can be leveraged to run your code. I try to split that into categories. The main one most people know about are what we call eager. The idea here is every operation you do is very elementary. Everything happens instantaneously. So every line of the code happens one after the other. It's what I would call the most straightforward way and what most people use. And we have quite a few of these. And the second big category is compiled. And that is if you used JAX or these kind of frameworks where it takes all your code and it's going to translate that into some pre-compiled binary that's going to run as a single thing. So there is a lot more distance between your code and what actually runs on the machine. And these days, we also have a lot of things in between. And what I mean by a lot of things in between is we're doing more and more just-in-time compilation. So even if your backend behaves like an eager backend, you are actually compiling under the hood at runtime. And you can do a lot of these things. So it is not 0, 1, but a whole spectrum in the middle. So what would be an eager backend? I think we have two categories of them today. There we have what I would call a device backend, which are what you're using when you actually use PyTorch code, and you pass in the device argument to a lot of our factory functions. It's a lot of low-level information implementation, and can be either in core, out of core. It must follow a lot of the definitions. So good examples here are CUDA or CPU or objects like that, that I'm sure everyone here knows. And also a lot of these that exist out of core, like HPU and other things like that. And they can be accelerators. A very different one that we are looking into more recently is what I would call a tensor backend, where instead of integrating as a device, as a concept of a device, you could integrate the concept of tensor object. And so you don't need to define things like how to allocate memory or things like that. You just need to say, this is a tensor object, and you need to provide something that behaves like a tensor. So it's a much higher level implementation, but it's going to integrate very differently with user code. The one that we tested very recently is we were working with tinygrad, and we were playing on like how to use tinygrad as a backend for PyTorch, and how can we, as smoothly as possible, translate from these two things. Compiler backend, I'm going to go very quickly because this is not my specialty, and it is very, very complex because it is a very active area of research today. There's a lot of new deep learning compilers, deep learning languages that come out every other month. And they go from working at the Python code level, so I would say all the way up, and trying to read the Python code or read even sometimes higher at the PyTorch NN module level. They just read the NN module, all the way down to generating code for CUDA or for accelerators. If you are one of the person working in this domain, my suggestion would be reuse as many of the existing pieces as you can. That whole story is very big. There's a lot of things in there, and components exist for different places. So focus on the part that you are good at and reuse the right pieces for everything else. So we have this very nice diagram from a while back for PD2. So this is the PyTorch compiler system. Here would be the user Python code all the way up. And then lowering is what we call lowering, which is translating into different compiled system, all the way to here where you actually generate the code that is going to get compiled and run on the accelerator. A good example here is you can see NVFuser, which is, for example, a compiler by NVIDIA, is integrated after Dynamo and IoT AutoGrad, which are components that are very high level that deal with how to read Python code in all of its complexity in a very safe manner. This one deals with AutoGrad and higher level systems, and then you can integrate your compiler below. That means you don't have to rebuild a front end that is going to be, that needs to be safe, that needs to work with everything. You can reuse these components that some people have spent a lot of time to build. Now I'm going to go in a little bit more detail into the device eager backend, because I think that's the one that is the most interesting that we have. So an interesting question here is what makes a PyTorch backend and what makes a device? And if you have to define all the work that is needed to add a new device to PyTorch, what would that be? So the key components I would suggest are a lot of low-level scaffolding, which are allocator, RNG, stream, device. So all of these are C++ components that need to be implemented at very low level, and that are usually done by a compiler team or a hardware team. There's a second piece, which is the one that most people know about, which is the operation coverage. So this is the actual implementation for all the functions you care about, like addition, convolution, matrix multiplications. Today, PyTorch has something like 2,000 or 3,000 such operations. So it is a lot of work, but they're not needed everywhere. So it is a big piece, but it is it's an easy piece to get bogged down into, even though the other ones are often more important. The third piece is the Python binding and front end, which is how do you expose the APIs to use your device? And that is surprisingly a lot of work that people don't usually know, because you think about all the operation you need to implement, you think about how your user uses your device, but you often forget that there is actually quite a lot of logic that binds the two together. The fourth piece is about domain support, which it's not the best name, but the idea here is like there are a lot of components beyond PyTorch core that needs support. The first one is most obvious, is distributed. So if you're an accelerator and you have a whole bunch of them and you want to connect them, use them together, you are gonna need to support different distributed systems, all of things like that. That is a new integration you need to build. Automatic casting for low precision, AutoGrad, memory pinning, all of these kind of things. And finally, and not the least, testing. Because it's one thing to get a new backend to work today. It's a lot of work, but it's one thing. But keep it running and evolving alongside the PyTorch code base is a lot of work. And testing is especially important to be able to do that well. To give you an idea, I think these days the PyTorch code base is 100 commits a day. So if you want to maintain the pace and have your backend follow, you need testing, you need automating system to follow the same pace as the repo and make sure that nothing new is going to break you, or at least to know what breaks you, because you will not be able to follow every single pull request. Trust me, I've tried. Now, that is a lot of things and very overwhelming. Hopefully, we've built a very important piece to improve that, which is how to build a device backend with what we call private user one, which is our out-of-tree extension system, and accelerator, which is adding a unified API on top of it. So this is pretty much the same slide as before, but there are a couple of things you don't need to worry about anymore. So the biggest one being all the Python connections, and a lot of the domain support goes away. The reason is we abstracted away in this accelerator concept, a concept of accelerator next to the CPU, and then we can build integration into a lot of these systems that is generic. And so you don't have to go and add support for everything yourself. Also, testing has changed quite a bit. You don't need to figure out what to test because we now, again, within this idea of accelerator, have a whole system which is OpenFOW and device generic tests that allow you to run tests on everything. One thing here we'll mention is OpenFOW, which is a very abstract name, I guess. The idea is very related to the op that we have here. And so OpenFOW is actually a database of all these ops, example inputs, example outputs, and properties of each of these operations. That sounds simple, but it is actually a massive undertaking to build and to maintain. But it is amazing for testing because to give you an idea, the test to make sure that our CUDA backend output the same result as our CPU backend is actually 20 lines of Python to cover every single of the 3,000 ops we have. Because we can just do a for loop over all the database of OpenFOW, go over every sample, and just make sure that running on CPU, running on CUDA gives you the same result. So when you're writing this kind of backend, it is, again, 30 lines of Python to just check whether your backend outputs the same thing than a CPU reference implementation, or even a NumPy reference implementation. So that is an amazing, amazing tool to test these things. If you want to learn more about that, we did a full end-to-end example that is fully featured multi-device backend. It leverages our implementation so that we have full coverage of these operations. We didn't have to re-implement everything in there, but it uses the out-of-tree extension points so that you can check all of that. And we actually have it in core. The link is here. And we use it for testing, actually, and make sure that this feature remains stable. All these extension points that we provide are here and are going to work well. So if you want a good reference implementation on how to use these extensions, this is a very good one. And there are many other users I don't know about. So I wanted to quickly mention here, there is an interesting key philosophy for this out-of-tree device system, which is in the best case scenario, I don't need to know about people using it. Because the whole point is to actually write an extension point that is for everyone to be able to use without us having to help you or us having to block you. And you can do everything by yourself. So it's been very exciting to see a lot of people build on this feature and do a lot of new things. I did a few more details, but we have a lot of extension points. We have automatic loading of systems so that you don't need to import everything. So very, very exciting. And so to quickly close, a couple interesting things that I wanted to mention for people that I think are super cool features, but sometimes people missed that they were released. So a great one is memory profiler. So if you've debugged memory issues or a problem with OOMs in PyTorch, this is an amazing tool. So there is a link here to a blog post with a lot of details. So this is, I won't go into the details, but it will give you a timeline with the memory usage, where you can see exactly, whoop forward pass, backward pass, how everything evolves. For every item in there, you can actually get a full stack trace on where that specific tensor was created, where that specific tensor is going to get deleted, so that you can actually easily track where in your code are these things being created, deleted, where things are happening. There is a visualization for it. You can visualize memory fragmentation. You can visualize all of these things. An amazing tool. I would highly recommend looking it up. Next, we are doing a lot of work to improve what we call custom ops. Custom ops is basically the tool you have to create your own PyTorch native operation or to extend or update any of the PyTorch native operations. The benefit of doing that is that your operation will then work smoothly with everything else in the ecosystem, that being the compiler that we have, but also with other systems that are like distributed or Hugging Face model, all of these kind of things. In particular, we added a lot of new features to register these things, to override the implementation that we provide if you have a better one. We added, again, a testing system called OpCheck, so that you can verify that your operation is behaving well and it's going to work well going forward. And all of this is available from both Python and C++. So depending on your need, depending on what you're trying to build, you hopefully should have full control of everything you want. And I actually skipped, we also have the Triton kernels as a native op as well. So if you're writing Triton kernels, if you are into these kind of things, there is native integration for these kind of things. So your Triton kernel will also work well, in particular with the compile mode. And finally, one that I was surprised by when we had this discussion with some colleagues 6 months ago. We were discussing like, how does CUDA pin memory work? And it was interesting, after 10 years of working on CUDA, actually no one got it right. So we actually wrote a whole very, very long blog post just to discuss that. Because it turns out it has some very surprising behavior. Very quickly, the 3 key takeaways. I would highly recommend reading the blog post in detail, but be careful about CPU side synchronization, because pin memory, for those of you who don't know, allows you to do asynchronous copies with the device. The problem is, this is well handled on the CUDA side, but on the CPU side, everything is usually supposed to be synchronous. And so it is actually not behaving as you would expect. So you need a lot of CPU side synchronization, which you usually do not need in PyTorch. So that can be very surprising. To profile to make sure that what you did works the way you intended. Surprisingly, using pin memory wrong is actually a lot slower than just doing the regular .CUDA or like just a regular copy. So don't assume that because you are using pin memory, things are always going to be faster. Do profile, do some testing, make sure it actually does behave the way you want it to behave. And finally, this is a bit more of a general statement, but using stream and events properly is very hard. We have a couple blog posts on the website and on the Dev Discuss, talking about these kind of things, how stream events work with the cache allocator. I did a rather long presentation at GTC about that as well. There's a lot of complexity there. So if you're interested, it's a very interesting topic. If you just want to use things, be careful and make sure that you test your code well. And finally, do share your feedback. So we do build a lot of things, and we're working with a lot of people to build a lot of things. We have quite a few channels of communication if you want to share your feedback. General discussions on the Discuss forum, GitHub for issues and feature requests, the Dev Discuss forum that I mentioned a couple times. This is where we have all of the more PyTorch core developer discussions. So don't hesitate to send a post there or read what's there. We try to have a lot of the long form discussions between maintainers is happening on that forum. And finally, if you want to contribute to PyTorch beyond Korea, we have this long guide that explains everything and everything you can do. And thanks for listening. Do you take questions?
알려주시고요. 손 드시면 네. 네.
Thank you for your talk. I'm Song Kim. I'm working for fintech company. I'm interested in AMD ROCm, AMD version of CUDA. How do you think about ROCm?
ROCm is it's a challenging backend. I think the long answer would be, there's a whole history on how we got here with multiple backends. I mean, where we are today is we're trying to build this accelerator system and this multi-backend system for PyTorch to make it easier for these backends to be all as good as each other. ROCm in particular, I think we have good base integration, but there are a lot of performance and usability questions there that have been happening. We need a lot of hardware and a lot of engineering time to fix all of these, and it is, one of the problems I was mentioning on like the ops support and on the testing is that this requires a lot of manpower to build and to have broad coverage. And unfortunately, today, the way things are going, we have more and more LLMs and more and more concentration on a small set of tasks. And so it is harder to find the resources to make sure that everything else works as well. So it is a hard balance.
Thank you.
부담 갖지 마시고 한국어로 질문해 주시면은 저희 번역 자원봉사자분이 계십니다.
Thank you for your talk. I'm a hardware engineer in Supergate. Anyway, my question is, from your experience, there are lots of custom MPU or accelerators in the market, but where do you think they struggle the most? What's the biggest painful blocks that hardware engineers struggle to, upstream to the PyTorch? Is there any specific experience that you, yeah?
I think there are two things. There is one that there is this interesting cycle where, because most people have CUDA device, most people write their code to work on CUDA, and so most things work on CUDA, and the cycle continues. And so when you have these new accelerators, you need to break that cycle to get people to write code that is not CUDA specific. And that is, as of today, very hard, or at least as of very recently, that has been very hard, because to get your code to be as fast as possible or very good performance, you had to use CUDA-specific APIs, even within PyTorch, to get there. So that's what we're trying to change a little bit with the accelerator concept. So we are trying to build this shared abstraction so that you can get more device-generic code out there in the wild. I think it's something that Triton is helping a lot with as well, because it's allowing to have one kernel that can run on multiple hardware. So that's one direction. There's like a lot of things today, for no good reason, don't work outside of CUDA. I think the other thing as well is hardware availability for developers, I would say. It's like a lot of the problem to build the systems and keep them running is to have people using them daily and using them for the tasks that people do, especially when you have a broad community. And for that, you need hardware and you need people that use this day to day. And so I think it's in a different way, very similar to what happens to our Windows backend. It's like very few people use it day to day. So it works, but you don't have as much feedback on how well it works. Or when it's broken, you don't hear as soon, as often. So I think a lot of these NPUs have the same thing. Is if you have less users, you have less feedback, and so less stability.
I want to ask more specifically, but so as a PyTorch core maintainer, what do you think? When do you feel the project can be integrated into PyTorch? So beyond the hardware's bare metals performance, what do you think? Okay, this is how does PyTorch maintainer think we want to integrate into PyTorch? What will be the critical reason? Yeah.
That is a great question for Jerry. Sorry. This is something that I think there are two big different pieces here, which are PyTorch core and the PyTorch ecosystem at the more foundation level. So I think the way I am thinking about this now is more like how long do you expect that project to be there and continue and expect to continue. And I think anything in PyTorch core, I would say, we would like it to work for at least 5 to 10 years. So if you want to send something into PyTorch core, you kind of sign that contract that you have to maintain it for the next 5 to 10 years. And it is a very hard contract to put on most people. It is important for the users to be able to reliably use it though. But there are a lot of things that need to move faster. You need to experiment, try new things. And so I think that's where the broader ecosystem that Jerry presented a little bit is very strong, because there we can have different projects moving at different pace. And on the foundation side, we are working with the technical advisory committee to have a process to onboard different projects into the ecosystem, into a platform, so that they can basically, as they mature, get closer and closer to the PyTorch core and PyTorch ecosystem. So we have this process on the foundation side. From PyTorch core, I would say it's more of a very technical discussion on like basically what is the feature, how long we expect it to remain there, and how stable it's going to be. That's how we differentiate the two.
Thank you. 예, 시간이 좀 부족해가지고 오늘 그 Q&A 여기까지 진행하도록 하고, 저희가 그 행사 끝날 때쯤에 저희가 30분 정도 오늘 세션에 이제 발표하신 분들과 그 다음에 그 참석자분들 간에 좀 Q&A랑 그 다음에 네트워킹 시간을 좀 가지려고 합니다. 예, 그래서 그때 조금 더 궁금하신 게 있으시면은 물어봐 주시면 좋을 것 같습니다. 예, thank you, everyone. Okay.
Thank you. Yeah.